Hello, thank you for joining our part two of our deep learning design patterns with TensorFlow virtual training. This is put on by Google Cloud AI Developer Relations, and my name is Andrew Froelich. I am a staff member of Google Cloud AI. Um, in part one, we introduced you to deep neural networks, and in this episode, we're going to be introducing you to convolutional neural networks. A convolutional neural network, to think of it in a simple way, think of it as it being a front end to a deep neural network. For example, like this. Previously, we discussed how we could do a simple image classification with minced images on a neural network. But the problem is when we get to really big images, that's not going to work. And we'll discuss that very shortly. So in this sense, what a convolution does, instead of learning pixels, it's going to learn features. And we call this feature learning. And that's going to end up with something of a much lower dimensionality when we go into the back end or the deep neural network where we're going to do the classification learning. So let's kind of address why we need convolutions. Right? So until we really discovered convolutional neural networks, it wasn't really feasible to do real world images. So think of your mobile phone and you take a picture. Typically, it's going to be at least a 1 megabyte image, and that's like 1 million pixels. Now let's imagine at our input layer, we would have 1,000 nodes. Well, if our image is 1 megabyte, that means we have an input vector 1 million elements long. And if our input vector is 1,000 nodes, every one of those 1 million elements is connected to every one of those 1,000 nodes. And that would be just over 1 billion connections just between the input vector and the input layer that we would have to update and learn during training. Let's contrast that to the minced example we showed in part one, where our input vector was only 784 pixels and our input layer was 512 nodes. In that case, there was 400,000 weights to learn. That is considerably smaller than 1 billion. So somehow we are going to have to reduce this very high pixel space into something more reasonable. Well, one of the first things we can do is upstream from the model, we can resize the image into a smaller image so that we have fewer pixels to start with. And what we have found is that convolution neural networks for image classification do a really good job down at the resolution of 224 by 224. So we could take this one megabyte pixel, hypothetically with an input layer of 1,000 nodes where we'd have 1 billion weights, and simply downsample it or resize it to the smaller size 224 by 224. In that same scenario, we would only have 154 million weights to learn. So we've already got it down considerably, but that's still too much to learn from. So training on real world images was, for all practicality, out of reach until the discovery of using convolutional layers. And what convolutional layers, it allows us to transform images from what we could say a high dimensional pixel based to a substantially lower feature-based image. So what does that mean by high dimensionality and low dimensionality? Well, 1 billion pixels or 150 or simply 154 million pixels is a large number, and that's what we mean by high dimensional. So in contrast, what we want to do in convolutions is we don't want to pull the pixels out, we want to pull out features. And that the features we're pulling out is a substantially smaller number, or what we say a lower dimensionality. So what is a convolution? Well, convolutions do what we call feature detection. They're going to look in the image and detect features. So let's make an analogy with how a human might do it, okay? So let's say initially we would look at an image and what we see are edges and patches. And this is sort of our coarse level feature detection. Then we would go through a convolution and take that input, not the image anymore, and again, pull features out of that. In this case, it might be contours. So we might see this, this, and this, these shapes. Then we take those shapes and again, detect features from them, say spatially, and then we form objects such as this, the human eye. So we started from this and we end up to that. And this is our lower dimensional space. So we're classifying features instead of classifying pixel positions. So in a convolution, convolution layers, perform the task of feature detection within an image. And the way it does it is it uses filters. And these filters are little matrices that are dragged across the image. And each one of them is used to detect at every location in the image the likely presence of a feature. And for example, at one location, if it detected the value of 4, and at another location, it detected the value of 1, in a sense, it's the first one is saying, I'm 4 times more confident that at this location, I've detected the feature than I am at the other location. So filters are learned, and this is what's kind of different about deep learning. The idea of having filters and sliding them across the image to detect whether there's features there is not new to deep learning. It already existed in the imaging science prior to deep learning, but these filters were hand designed. And typically, back then, it took a room full of PhD people and a lot of money to come up with a good filter. Today, filters are learned. So in a sense, they actually start off uninitialized. They don't know what feature they're going to detect. And as you train the model, that filter itself is going to be continuously updated and learn to be an effective feature detector. Now, in convolutions, these filters, we typically they could be any shape, rectangular shape, but today we always make them squares. That is the height by width is the same. And our typical sizes now are 3 by 3 and 5 by 5. And 3 by 3 are the most common. At each convolutional layer, we also have number of filters, not just one. So each filter is going to learn to detect different features at that level in the convolution. So typically filter numbers are multiples of 16, and this has a lot to do with hardware. That size is the most efficient size for hardware utilization. And when we talk about shallow networks, they're typically multiples of 16, around 16, 32, or 64. But when we get into deep convolutional neural networks, you'll see number of filters around 256, 512, and 1024. Okay, so this picture here sort of gives you a little bit more detail of what happens when we take a filter and we're going to slide it across the image. And what we're going to do is for every filter, we're going to build what's called a feature map. And that feature map is going to hold the values of how strongly we detected that feature at that location in the image. And that feature map is going to maintain the spatial relationship back to the image. So for example, whatever I detected in this corner would be in that same corner. What I detected in this corner would be in that corner. And everything in between would be proportionally or spatially in the same position. Now, the other thing important here is what we call stride. How fast do I move this filter across? So let's say this is a 3 by 3. If I move the filter 3 pixels at a time, I would have no overlap. If I move the filter 2 pixels at a time, each time it would overlap one column. And if I moved it 1 pixel at a time, it would overlap 2 columns. And this is referred to as the stride. And in practice, the most common strides are 1 and 2. And it turns out, and I'll explain in a moment, if you use a stride of 1, the feature map on this size is essentially the same size as the original image. If you use a stride of 2, it will actually half the width and half the height. So the next thing people tend to think of, okay, let's go back here. I'm sliding this filter across the image, and I go down the next row, slide it across the image. What do I do when I get to the edge here? And that's referred to as padding. Do I stop at the edge or do I slide over? Well, in some cases, you may want to stop at the edge, and we tend to call that no padding or valid. In other cases, let's say we're doing a stride of 1, we're going to keep moving the filter across until we get to the last row. But the problem with that, of course, is part of the filter is outside of the image in what you might call this imaginary space. And the question is, what do we put in that imaginary space? Well, the common convention today is to simply copy whatever is here into this space here, the imaginary space. We call that the padding. And if we copy this into the imaginary area, we call that same padding. So another way to think about filters and strides is they're also a trade-off about how much data you're going to have. Remember that as you go deeper into the neural network, the more data you have, the more parameters you're going to have, and the bigger your model is, and the longer it's going to take to both train and do prediction. So we're always trying to do some trade-off of having enough data to get high accuracy, but not too much data as to make it too computationally complex. So one of the trade-offs is as we add more filters, we're adding more data. But on the other hand, if we increase the strides, we're making those feature maps smaller and smaller, and we're making less data. So we're going to be looking for some trade-off between the number of filters and the stride size. So when we talk about making the feature map smaller, this is sort of falls into the area of what we call downsampling. And there are 2 types of downsampling. One of them is called pooling, and the other one is feature pooling. Now, pooling is a fixed algorithm that is used to downsample the size of the image data. Essentially, it's very much similar to what we talked about earlier about upstream resizing your image. And that's effectively all it's doing. It's using a fixed algorithm to resize the image to a smaller size. The other version of this is what we call feature pooling. And that's when you use a stride greater than 1, like a stride of 2 on a convolution. The feature map that comes out is going to be smaller, but the difference here is we're not using a fixed algorithm. Instead, we're learning the best sampling algorithm for your specific data set. So let's just start talking about pooling the fixed algorithm. Okay, so we're going to generate, let's say at our first convolution, we're going to generate multiple feature maps, let's say 16. And each one of these feature maps initially is the same size of your image. Well, our total data size has gone up. Instead of having this one image of this size, I really got 16 of them. So now my next step is I want to reduce the total amount of data while retaining the features detected and the corresponding spatial relationship between the detected features. Well, this step of pooling can be done 2 different ways. One of them is we could do what's called max pooling, and the other one mean pooling. In max pooling, we're going to have, in both cases, we're going to have a little window that we're going to slide across the image. And at every location in that window, if we're doing max pooling, we're going to take the biggest value in that section, and that's what we're going to replace it with. Or in mean pooling, we're going to take the average value within that window. So let me show you an example here. So let's say these are the feature maps we generated from a convolution. And we have a window, and let's say it's going to be a 2x2 pool size. And we're going to have a stride of 2. Right? So we're going to drag it across here. I'm going to go down, drag it across, go down, drag it across, go down. At every location, we're going to look at what's inside the values in here. Since this is a 2x2, we're going to be looking at 4 pixel values at a time in our feature map. And in the case of max pooling, we're going to take the value of these 4, that's the highest value. And we're going to use that value put it into the same identical location in what we call the pool maps. Now, because we use a stride of 2, these maps are going to end up half the height and half the width. And that means we're going to reduce the amount of pixel data by 75%. And in general, at this reduction, we're still able to preserve enough resolution that the detected features are not lost through pooling. So we've done all these convolutions. We generate feature maps, we pool them into a smaller size, we generate more feature maps, we pool them into a smaller size, we generate more feature maps, we pool them into a smaller size. And by then we say we have that fine level of feature detection. And now what we have at this point is not pixels, but features. And we're ready to go into the back end and do our classification learning. If you recall in part 1, when we talk about a deep neural network, its input is a 1D vector. And here we have feature maps. So just like we did in the minced example, where we had one image where we flattened it, here we have multiple feature maps, and we need to flatten all of them into a 1D vector. Essentially, it's the same thing. We start with the first feature map and we flatten it. So it's going to be here. And we take the next feature map and we just flatten it right behind it. And we keep repeating that until the last feature map. So we end up having this long, flattened 1D input vector. And that is what we're going to input into the deep neural network for classification learning. So let's go ahead and start coding a simple example up here. So from Keras layers, we're going to import the convolution 2D, okay, and the max pooling 2D layers. You should already be familiar with other layers such as flattening, flatten, dance, ReLU, and our activation. And in this example, we're going to pretend our inputs are images that are 128 by 128, and they're grayscale. And we're going to use a stride of 2 to reduce the size of these images while we're doing the convolution. Recall that form of pooling we call feature pooling, where we use the convolutional layer to learn the best way to reduce the size of the image. So here we're going to create our model, and it will, when we instantiate with the sequential class, we get an empty model. That is, it has no layers. And we're going to start here adding the very first layer. And in this case, we're going to create a conv2D. Now, you may ask, what's with the 2D? And that just says that's the input shape coming into the convolutional layer. But it's the input shape of what we call each feature map or channel. Because it's not unusual for somebody to ask, well, if I did an RGB image, isn't that 3D? I got these 2D matrices, and then I got 3 of them. And that's correct in that sense, but this simply refers to the size of each one of those channels. And so in that case, with the RGB, you have 3 channels, but each channel is simply height by width, which is 2D. So our first argument here is the number of filters. I'm going to generate 16 filters, or more specifically, not only generate, but learn the 16 filters. Then there's my kernel size, which is the same thing as filter size. So that window we're going to move across the image is going to be a 3 by 3. Then comes my stride. I'm doing a stride of 2, which means I'm going to, as I move across the image, I'm going to skip every other pixel. So that's going to reduce the size of the outputted feature map to be half the height and half the width of the input here, or 75% smaller. My padding equal to the same, just says what do I do when I get to the edge of the image? In this case, I'm going to keep going over the edge until I get to the last column that I'm overlapped with. And in the imaginary space, I'm going to just copy that last column of data into the imaginary space. And of course, since this is my first input layer, I have to specify the input shape of the input vector. It's going to be 128 by 128. And you may notice I added this comma 1. Even though this is a grayscale image, the conv2d requires you to specify how many channels you have. And so therefore, grayscale images have 1. So I'm going to go comma 1 here. If this was an RGB input, this would have been comma 3. 1 for red, 1 for green, and 1 for blue channel. So let's continue on. So now I have these feature maps coming out. I put them through my rectified linear unit, and I want to reduce their size yet one more time. And this time I'm going to use max pooling 2D. Again, the 2D to refer to the size of the shape of the feature maps. And I'm going to set my pool size to 2 by 2. So my window is 2 by 2. And my stride is a stride of 2. So I'm going to again be skipping every other pixel. And so the output of the max pooling is again going to be 1/2 the height, 1/2 the width of what came into it. And then those smaller feature maps, I'm going to flatten into a 1D vector. And now I'm ready to take that 1D vector and input it into the DNN classifier backend. And this just shows a simple backend here. This little example I actually wrote for a data set. It was a grayscale data set of images 128 by 128 that were hand signs of the English letters A through Z, which there are 26 of them. So it had an input layer at the DNN of 512 nodes. And then the output layer was 26 nodes, 1 for each letter in the alphabet. And of course, a softmax, since this is activation, since this is a multi-class classifier. Now, let's take that model and invoke the summary method on it, and we'll get this output. And if you look at this output, it looks quite a bit different than it did when we were doing a simple DNN. So here's the first thing to notice. This last number here is the number of channels that are coming out of these layers, and that corresponds to the number of filters. So let's go back here. You said there were 16 filters, so we're going to have 16 feature maps, or the same word, channels means the same thing here. So there's our 16, okay? This part here is the shape of those feature maps. Now notice there's 64, 64. And the input coming in was 128 by 128. But we did feature pooling at the first convolutional layer, which would therefore change the size of those feature maps to be 1/2 the height, 1/2 the width. And that was how we got 64 and 64. And then we went into max pooling. And again, we set stride equal to 2, which means the output is going to be 1/2 height, 1/2 width of the 64, 64. So that's going to be 32 by 32. We now flatten that, and so we take that 32 by 32, and we take 16 of them. We're gonna have a 1D vector that has 16,000 elements in it. Now, our input layer is 512 nodes. So every one of these elements is going to be connected to every one of these nodes. And that already gives us an explosion of numbers. We actually have over 8 million parameters. So even in this extremely simple model, we have to update and learn 8 million parameters. So let's go ahead and rewrite that CNN. And this is actually known as a basic sequential CNN. The style is sometimes called a convnet. Okay, but we're going to write it in the functional API approach now. So here we're going to start off with instantiating our input object. And notice this time I also, unlike when we did with a DNN, I'm adding in the number of channels. This case is 1. Then I create my first layer, the convolutional layer. I got my 16 filters, my filter size of 3 by 3, my stride of 2, my padding, my activation is a ReLU, and then I'm going to tie the input vector to the input layer. Then I create my max pooling layer, and I'm going to tie the output of the conv2d layer to the max pooling layer. I'm going to then add my flatten layer, tying the output of the max pooling to the flatten layer. Add my backend, the 512 layer with the ReLU activation. Finally, the output layer of 26 nodes using a softmax activation. And then as a last step, I instantiate the model object specifying the inputs and the output. It follows those bindings and ties the model or builds the model. Okay, so at this point, we're going to start talking about some of the early state-of-the-art convolutional neural networks. And really, the grandfather of them all is what we'd call the VGG. And VGG introduced this concept of a design pattern. Okay. Oh, I'll back up for a minute. The VGG net is kind of important because there's this, if you're not familiar with, there's this annual international competition called ImageNet. And one part of the competition involves image recognition of 1,000 classes of images, and research and innovation labs all over the world would compete to be winners. And in 2014, VGG was the winner. Its name comes from who developed it, and it was the Visual Geometry Group at Oxford. So what they decided to do is come up with a pattern that is repeated over and over and over in the convolutional neural network. And so they start off with this idea of having convolutional groups. And in each group, the number of filters is always the same for each convolution, but they defer the pooling step to the end of the group. And then for every group, subsequent group, they would double the number of filters. So you start off with 124, the next one would be 128, the next one would be 256, and so forth. Finally, at the back end, they use 2 identical size dense layers of 496 nodes each, and then the final output layer of 1,000 nodes for classification. So let's go ahead and write a VGG. Okay, so we'll code it in 2 different styles. We're going to first start with a basically simple sequential flow here. So I instantiate my sequential object here. That gives me a model, an empty model. And I'm going to make my first convolutional block. And if you recall, or convolutional group, I mean, each group consists of a number of convolutional layers. All of them have the same size number of filters. In this case, I'm just going to have them each having 2 convolutions. So we start off with 64. This being the very first convolution, of course, is we have to specify the input shape. My next convolution, I'm going to double the number of filters, and again, end with a max pooling. And then I kind of just remove the rest of this code for brevity. This pattern keeps repeating itself until we get to the back end where we do the flatten, and then we go into our dense layers. Now, you may notice that since this is a pattern and we're all good programmers, why shouldn't we? Maybe we can just put this into a function and do reuse, procedural reuse. Drink of water. So, being good programmers here, we go ahead and we write it procedurally, doing reuse here. And what we know is every one of these groups consists of a certain number of layers. And for every layer, we're going to have the same number of filters. So we just pass in how many convolutional layers we're going to have in the group and how many filters for that whole group. So we'll spin around here and just add that many convolutions, always with the same number of filters. And when we're done, we add in the deferred pooling step, in this case, the max pooling with a stride of 2. So let's go ahead and write the front end of a VGG before we get to the back end. So we create our empty sequential model. We're going to add the first layer separately simply because we need to specify the input shape. Then that remaining the first group has one more convolutional layer at 64. The next group had 2 convolutional layers at 128. The next one had 3 convolutional layers at 256. The next one, 3 at 512. And the last one just simply repeated that. And really, this is all the code it takes to write the entire front end of a BGG. So the next really important thing that came along was ResNet. And ResNet took first place in the 2015 contest in ImageNet. And just back up for a minute. One of the problems still with the VGG is, you wanted to go deeper and deeper and deeper with layers, because as we added more layers, we'd get more accuracy. Well, back then, if you went too deep, you would actually have the opposite happen, and you would get what's called degradation. It would actually get worse. And there were multiple reasons for this. Okay. One of them was called the vanishing gradient. Okay. And if you recall that with these weights, they tend to be tiny numbers, generally numbers less than 0. And if we multiply 2 numbers less than 0, we get another number that's even smaller. And as we go deeper and deeper into neural networks, the more and more likely we're going to have tinier and tinier and tinier numbers. At some point, those numbers can get so small, your hardware can't represent that number anymore. And boom, everything stops. And that's called the vanishing gradient. And in this contest, we're talking about it at training at float 32 or 32-bit floats. We have found that we can get comparable accuracy training at 16-bit floats, a half of precision float. And you can execute 4 16-bit instructions in the same time as a 32-bit. So if you can train at that level, you can train your model 4 times faster. Well, with a even smaller hardware representation, you're going to hit the vanishing gradient even sooner. The other problem we ran into was called the exploding gradient. And this is when the values of weights just had a bigger and bigger spread. So one part of the model, the weights are very large, and another part of the model, the weights are very, very tiny. Well, in that case, the updates to these weights are so overwhelming in comparison to the tiny ones, it just sort of masks them out. It really makes them disappear. And so part of your model, in a sense, dies off just because of those real big weights. And again, the degradation. Well, ResNet the design of the ResNet helped reduce that and be able to go even deeper into neural networks without the degradation, and therefore that's why it won the 2015 contest. So the original ResNet pattern, referred to as a ResNet 34, introduced a new block layer and connection pattern. And excuse me, it was referred to as a residual block with an identity connection. And the block consists of two identical convolutional layers without a pooling layer. And then each of these blocks had what they called an identity link. And that is a parallel path from the input to the output. And what they would do is they would add the input to the output. And then each successive block would double the number of filters, just like it did in a VGG. And at the end of the sequence of blocks, they would do the pooling. Again, defer the pooling to the end of the sequence of blocks, which makes it a group. So this is a visual representation of a ResNet block, a ResNet 34. So as I mentioned, it would consist of two convolutions. They were 3x3s. This is your input. Okay, the output from those convolutions, this is your identity link. So we're going to save a copy of the input. And what we're going to do is we're going to do a matrix add of the input to the output. And this is what they meant by feature reuse. So prior to using identity link, like in a VGG, when you went through blocks or groups, in a sense, you're forgetting everything that you knew at the input. You're only working with the output. And so as you go deeper and deeper and deeper, you lose memory or information about earlier stages. And the idea with the residual block is to retain some of the past on the output here. Well, this style resulted in more stability in the weights in the model, as far as how small they got or how far they spread out. And therefore, they were able to go even deeper in layers without degradation and get higher performance, in this case, accuracy. So let's go ahead and code a residual block in a functional API. Now, it may seem, when you look at this picture, a little bit scary. How do I do it? It's actually really easy. And this is one of the advantages of residual, of using the functional API, because you can do non-sequential flows, for example, a branch. So let's start off. Let's say this is the entry into the block, and we want to remember the input. So we're going to call that the shortcut. We're just going to remember what the input is. We'll do our two convolutions. Then we have our output here, X. And then we're just simply going to do a matrix add, and we're going to add the output to the input, or conversely, the input to the output. And that's it. We just now wrote a ResNet 34 block. So these few lines of code is identical to this picture here. Now, you may have noticed, okay, I'm doing these blocks, I'm doing these blocks, I'm doing these blocks. Well, at some point, at the end of this group of blocks, we need to do our pooling, okay? And we're also going to have another problem. So at the end of one group, let's say it's 64 filters, and the start of the next group is 128. Let's go back to this picture. So in the second group, let's say we start with this block. Our input is the same number of filters from the previous group, that's 64, but these are going to raise them up to 128. I cannot do a matrix add of a shape that's 64 to a 128. This shape has to be the same as this shape. So between groups, these ResNet groups, we need a convolutional block connector. And it's going to perform two jobs. One of them is going to do the deferred downsampling, and it's going to do the feature expansion so that the number of filters going into the next group is the same number of filters that are used by that group. In that sense, it's going to simply double the number of filters. So if we were writing this and we took that previous code sequence and we put it in a function, we'll just call it the residual block. And so we just spin around for how many blocks there are in that group. And then before we start the next group, we just create a convolutional block specifying the number of filters. And in that procedural reuse, we'll do a convolution that will expand to this number of filters, but at the same time do feature pooling, reducing the number of features. So let's go ahead and show what that would look like. So here is our residual block. Here's that little bit of code that we did earlier. So you can see how I just put it in here. I'm just passing in the number of filters. Every ResNet 34 block would have 2 convolutional layers. And then it would remember the input and add the input to the output. Then the conv block has actually 2 convolutional layers. Both of them are strided, or strides of 2, which means they're both going to do feature pooling. In this case, this is where we're going to specify the number of filters to expand to. Okay. And what's interesting here is at the first convolution, we're going to reduce that size of those feature maps by 75%, which means they're only 25% as big. When we take the next convolution, we're going to reduce that 25% size by another 75% size. So actually what happens coming out of here is that the feature map sizes are actually only 6% as big as they were coming in. So this is a very aggressive pooling. The next thing that a ResNet did was it changed how it did the back end. Previously, I've been showing you that after we've done all our convolutions, we take all the feature maps and we flatten them into one long 1D vector. Well, in a ResNet architecture, particularly the one they took in the contest, when they got to that final step, the number of feature maps they had was 2,000. And the size of the feature maps were 4x4 or 16 pixels each. So if they'd done that, they would have had an 1D vector coming in, that would be 32,000 elements. And they used a single dense layer for classification 1,000. So you would have 32,000 times 1,000. That would have been a huge explosion of parameters just right on the final step. What they found is that all they really needed is they didn't need all the values in each feature map. They only needed one value in each feature map. So what global average pooling says is go to each feature map and get the average value, and then use that in your 1D vector. So each one of these feature maps is a 4x4 or 16 pixels. So it would look at those 16 pixels, average them out, and replace them with just one value, that average value. And so now my 2,000 feature maps, when I flatten them, become a 1D vector 2,000 elements long, where every element represents the average value in the corresponding feature map. And that's what global average pooling 2D does. Okay. So another thing about this design is that it was computationally faster. So let's go back to the VGG16. If we ran a model summary on it, we would get 138 million parameters to learn and to update and learn. In the ResNet, that was next year's competition and beat the VGG in accuracy, it only had 21 million parameters. That made it 6 times computationally faster. So by using this identity link, they were able to go deeper layers, get more accuracy, and be 6 times faster. Now, the next design, and is what we're really familiar with today, was called the bottleneck residual block. And that's typical of what you would see in a stock ResNet 50. This is a very common model people use, continuously use today, okay? And in the bottleneck residual block, it was what they call a refactoring of the ResNet 34. The goal here was, could I even further reduce the number of parameters in the block without a loss? In this case, they used the word representational equivalence. Is there a refactoring? Gives me less parameters, but is representationally equivalent to the previous version. And that's what they found in the bottleneck. They did a lot of experiments, and this is the one they came up with. So in a bottleneck, you have 3 convolutional layers. The first layer actually does a dimensionality reduction. Think of it as a bottle, the head of a bottle, of a bottle, okay, where it's very narrow, and that's what this does. And then it does a single 3x3 convolution on that more narrow or lower dimensionality data, and then it's put through another convolution that does the expansion. Also notice that the first and last convolutions are 1 by 1. And when people first see that, they're a little perplexed, because that means your window, uh, your little filter is a single pixel. And if you're dragging a single pixel across an image, how can you learn any features? And you're right, you're not learning features. So a 1 by 1 has 2 purposes. It's either to increase the number of filters, which we call linear projection. So you're expanding the dimensionality, or is to reduce the size of each filter or the number of filters, which we call dimensionality reduction or a bottleneck operation. Okay, so 1 by 1s are used to either expand or compress. Okay, and instead of doing it as a fixed algorithm, they learn the best way to either expand the data or compress the data. So let's go ahead and just write what a bottleneck residual block would look like. It's fairly simple to write. In this case, we have the 3 convolutions, the 1 by 1, the 3 by 3, the 1 by 1. So the number of filters is the reduced number of filters we're going to have. So that's the dimension that specifies the reduction in dimensionality. And the way the bottleneck ResNet was written, it was do a reduction of to 1/4. So here is our bottleneck 1 by 1 bottleneck convolution. Then we have our 3 by 3 convolution doing it on this smaller size here, so fewer parameters. And then the last 1 by 1 convolution expands the number of filters. That is our linear projection. So that's where we do our dimensionality expansion, or you could say dimensionality restoration. Finally, I'm going to take the input here and I'm going to add it to the output. So the last thing we're going to cover is batch normalization. So as I had mentioned already, ResNet allowed us to go deeper and deeper and deeper. But even with a ResNet, at some point when we went deeper, we still hit the problem of degradation. Again, we still hit issues of vanishing gradient and exploding gradients. It just took long. We could get further before that hit. So the way that eventually got solved is with an idea called batch normalization. And what that does is it's the recognition that as we go deeper and deeper in layers, these values are getting further and further spread apart. Okay. And what we want to do is squash them at every layer so that they stay the same distribution. That is, we want to stabilize them into a consistent distribution all the way down the model. And that's what batch normalization does. So the signals coming out of each layer are squashed into this more consistent distribution all the way through the model. And once we've done that, we basically eliminated the vanishing gradient and exploding gradient problems. And we were able now to suddenly go extremely deep with models and get extremely high accuracy. And generally, the convention today is that after every convolution and layer and dense layer, we would do a batch normalization. So let's take that to a real simple example here, where we have a convolution layer of 64 filters, and we take the output of it and we run it through a batch normalization, and then a rectified linear unit. So the signals here coming out, we're going to squash them back into the sort of consistent distribution. So then we flatten that, we do a dense, and again, that would spread it out. And so the output from the dense is we do another batch normalization. Again, we're sort of squeezing them into this more consistent distribution. Okay, well, that's the end of this particular part, or part two. We have a follow-up exercise on it, and we have a separate video how to get started on lab exercise 2. And again, thank you for joining us.